Hello again. We have defined the regression model for two regressors, which was straightforward. And then the next question, we learned how to interpret those parameters, which was also straightforward. And next, we need to think about how to estimate the parameters. The result is pretty much the same as before. So we remember the ordinary least squares estimator minimizes. Think about this. What we are doing here is we predict y by this functional form. So we predict y by carefully choosing these three parameters, and the difference is the actual value and your prediction. The difference is the prediction error, which you desire to be zero, and you want to make it as close to zero as possible. So you take square of the prediction error, which will be always positive unless the error is zero, and the error is summed over all observations. Then this is what you want to minimize. So the summation of squared prediction error captures the magnitude of the prediction errors that you will get when you choose these three parameters, these three estimates. B0, B1, B2 are your candidate for the estimates. You'd like to minimize the total amount of predicted errors by carefully choosing the best one that minimizes this. That is the motivation and motivation of the OLS estimator, which is the standard method almost for any standard regression models. And the idea is the same. It goes in the same way. So actually it is possible to calculate the first order condition. You can derive you can solve for the parameters beta 0, beta 1, beta 2, but you don't need to because STATA does it. So anyhow, the STATA results are based on this idea, and like Excel, STATA, R, whatever are based on this idea. And then if you estimate the model and apply the model to our example, test score and student to teacher ratio, when you had only one regressor, you got these two estimates, intercept and slope for the student to teacher ratio, minus 2.28. Now you include additional variable, percentage of English learners, then it turns out to have a negative impact, which is intuitive because as we conjecture that the higher the percentage of the English learners then the lower the test scores will be, because the more non-native speakers, then they are not good enough in English, then their test scores must be lower than their native counterparts. Therefore, the effect of percentage of English learners must be negative. This is good, but what you need to look at here is this number and those two guys. So the intercept and the slope for the student to teacher ratio were the same parameters as before as in here, but they have changed. So including additional variable changes everything. That's the importance of including all the relevant variables. So those difference, you can think this difference was the omitted variable bias. So after the inclusion, the effect looks like minus 1.1. Then where is the difference coming from? The difference came from the indirect effect from student to teacher ratio to test score through percentage of English learners, right? So the indirect channel from student-teacher ratio to percentage of English learners to test score is quantified as can be quantified as this difference. So the previous result minus 2.28 was underestimating the effect of student-to-teacher ratio, or it exaggerate the negative impact of, it overstates the negative impact of student-to-teacher ratio. Student-to-teacher ratio, actually it looks like student-to-teacher ratio does have some impact, but not as much as before. So that's what we can find after including another variable. So everything changes. That's the point. So you cannot assume it will be the same, like if you change the model. And also it's important to see the correlation between these two guys. So remember, I explained the indirect channel as the effect from student-to-teacher ratio on percentage of English learners times the effect of percentage of English learners on test scores. Let me go back to that page. Where was it? So this one. So you can understand this as this indirect channel is from a regressor to the omitted variable, and from the omitted variable to the outcome. This is student-to-teacher ratio. This is the percentage of English learners. This is test score. And the bias is the multiplication of them. So this times this, their product is the omitted variable bias. And think about this. You will get, if you multiply this, so this is, this captures the direction of the effect between student-to-teacher ratio on percentage of English learners. It is positive, and then the second channel is negative. So first channel was positive, second channel was negative, so the total bias is negative. Their multiplication is negative. By the way, it is not exactly what I meant by gamma, so I cannot calculate gamma only from this information, but the correlation tells you the direction of the omitted variable bias. So positive and then negative combined makes a negative omitted variable bias. And also, it is interesting to think about what happens if they are not correlated. Then if they were not correlated, then indirect channel is blocked. So the first step is 0. So then there is no indirect channel. So there would be no omitted variable bias. So there is no omitted variable bias even if you did not include this guy. So, right? So indirect channel, the first step of the indirect channel is 0. So you don't need to include this. It is not relevant in your analysis. And second, if it was 0, if the correlation was 0, then including this variable makes no change on this coefficient. Because remember, the difference is the omitted variable bias. And if there was no omitted variable bias, there would be no difference. Also, there will be no difference here. Excuse me. The intercept may be different, but the coefficient would not be different. So there is no omitted variable bias. So when there is no correlation between this and this, so it is another, it's another kind of brainstorming practice. And let's see what you get from STATA. So in STATA, first look at the code. Maybe later I will demonstrate STATA on like using the homework. But it's the code, STATA code is also, command is also straightforward. Regression, the REG is an abbreviation of regress. Regress, test score on student-to-teacher ratio and percentage of English learners. And they put option robust. When they put option robust, they got this result. Interpretation is the same. You know what these are, except for these two guys. So you know what the number of observation is, and R squared, root mean squared error. We learned what they mean. So same idea, same definition holds here. You can interpret them in the same way. So sample size is 420, and R squared is now 42%. 42% means the 42% of variation in the test scores is explained by those two variables together. So using those two variables, you could explain 42%. That's what you can interpret here. And the root mean squared error, which is called the standard error of the regression in the textbook, is 14, which means this is the standard deviation of the error term. The error term has a standard deviation of 14. So 14 points of test score is the standard deviation of the test score from the error term. And those coefficients are exactly what you saw before, and they are standard errors and t-statistic, p-value, confidence interval, typical things. And so I did it by myself. I also ran STATA regression without using robust option. So I did not use robust option to show you additional result. Remember, these numbers do not change. Coefficients are exactly the same as these numbers. You can compare. They are the same, but the difference is the standard errors. The standard errors are now different. It is 0.38. Previously, it was 0.43. So now robust standard error makes the this is correct. The robust standard error is correct, but this is wrong. That means if you are underestimating the standard error if you do not use the robustness option. And it may mislead, and as a result, it looks like t-stat is 2.9, but actually 2.5. So in this model, your coefficient is not statistically significant at 1%. At 1%, the p-value is 1.1%. So this is not significant at 1%, but it is significant at 1%. So this is wrong. So you can make a wrong conclusion when you do not use robust standard errors. So even though it is not that significant, you may conclude it is significant, so your interpretation could be misleading. Anyhow, that's about robust standard error. And what I want to show you here is look at the degrees of freedom. And the degrees of freedom, it was 1 when you had only one regressor. So remember, the sample size is 420 and the total variation is 420 minus 1 because the average was calculated, and the model has two variables, so the degrees of freedom is 2. And the degrees of freedom in the residual is total degrees of freedom minus the model degrees of freedom. So you have to subtract 2, which is the number of variables, number of regressors. And also we will learn this guy. In the single regressor model, it is adjusted R squared, but in the single regressor case, adjusted R squared equals R squared. So there was no difference between these two guys. But now, when you have more than one regressor, you are going to see the difference. So I will explain how they differ. Okay, I will continue, and the next one, see you there. Bye.